Hi, this is ET250 lecture 18, but a bonus lecture 18. Okay, and so in this lecture, what we're going to look at is an example of a transformer where we have a AC source and a resistive load. We saw this in lecture 17. We saw some weirdness in the simulation where the voltage ratio, even though the coupling factor was nearly 1, the voltage ratio and the current ratio didn't match nicely from what we would expect, right? So we're going to look at I2, this current here, the load current, as a function of the system parameter. So not just V1, but L1, N1, L2, N2, and M. We'll look at how do we choose L for different ratios, right, and different loads, okay? We'll look at a little Matlab script on how I chose the L, and then we'll look at a simulation to kind of confirm how different L's actually perform in the simulation. And finally, we'll look at a proof of this general crazy equation for I2 that we'll show here. Okay, well, let's begin. So very simply, we have a transformer, right? We have V1 by KVL, these are the same voltage, and V2 by KVL, these are also the same voltage. Simple resistor, I1, I2, two dots, great, and then L1, N1, L2, N2, M. Good, no problem. And so the question is, how does I2 depend on V1 if the coupling factor is not 1? And we're going to assume V1 is an AC signal, so it has some peak and it has some frequency. We'll ignore the initial phase. We'll just say it starts at a phase of 0 for now. But this is the amplitude and this is the frequency. Okay, and as time goes on, this thing is an AC signal. Okay. Now, by Ohm's law, this V2 equals I2R, right? No KVL going over here, positive. Yes, we're good. Okay. But by our mutual inductance equations, we also get that relationship, and we'll talk about that later. Now, if everything is ideal, if K were to be exactly 1, how would I2 depend on V1? Well, we know V2 equals N2 over N1 V1. And look at this, positive touching the dot, we're all good. And so what we would get is this. We get I2 is equal to 1 over R. That's from this. I2 is equal to V2 over R. Good. That's the Ohm's law. And then the V2 would substitute in the ideal transformer relationship. So you'd get this, 1 over R, N2 over N1, V1. And V1 would be the sinusoidal signal. So therefore, I2 would be a sinusoidal signal. The only difference would be is that the I2 would have a different amplitude. The amplitude of I2 would be VP times the ratio divided by the resistance. And that should make sense, right? It's just a scaled version. And they should be in phase in this case, right? So I2 and V2 are in phase, and V2 and V1 are in phase, okay? That's the ideal situation, no problem. But what is the general form? Like, where does the L1s come into play? Where does the M's? Where does the N2s? Where does all this stuff come into play? Well, if you are still interested, I will prove what this I2, this crazy expression, and is, and I'll show it to you right now. In general, I2 depends on not just these R's and N2s, N1s, and VPs. It actually depends on the coupling factor. It depends on L1 and omega, right? And the frequency. And this is the insane equation. And you look at this, and I look at it, and it's just like, oh my God, really? But it's not that bad. So let's look at it closely. Okay, so check it out. I have a cosine here. Okay, that's no problem. So that means and I have an omega t minus a phi. Okay, we know what that is. That's just a cosine that's just shifted by some phi. And look at this guy. This is, yeah, it looks nasty, but it's just an amplitude. So at the end of the day, this just becomes a constant number, all right? So you have just a sinusoidal signal for I2 as a function of time, and it's just phase shifted from the original source. Okay, so if this is oscillating and the peak is at 0 time here, it's phase lag, so it's a little bit later in time. Okay, so now we look closely at these terms. We have a K, a gear ratio or a transformer ratio. Weird, square root R squared. Oh, okay, so the units are going to be just 1 over R. That's looking very close to this. And now I have this nasty term, omega squared 1 minus K squared N squared over N1 to the fourth L1 squared gross. But look, I have that same term over here in this arctangent, right? And the only difference is this term here and this term here. This is just a squared version of this one, right? Omega squared, good, L1 squared, N2 over N1 squared, but this is to the fourth, 1 minus K squared, but this is squared. Okay, and then over R. All right, so all the terms at least are coming from here, good. And we will prove this later if you're still interested. You can see how I got this equation. I'm not going to present it right now, but for those who are interested, you can keep following the video. Okay, so let's just check k equals 1. If we actually set k equals to 1 in this, do we actually come up with this form? We better, right? If this is the general case, and this is a special case when your k is 1, we better reduce this down. Let's double check. So if k equals 1, that goes away, that's 1. Okay, what's going on inside here? Oh my goodness, that just cancels out. This whole nasty term goes away. Same with this nasty term. So you get a tan inverse of 0, which is 0. So the phase goes away, fantastic. And here, look at this. We get k times n2 over n1, or 1 times n2 over n1. And then you just get an r squared square root. That's just r. Oh my goodness. That's exactly what we're getting here. So that's good. That's a nice consistent result, is that this crazy equation actually reduces down to the ideal relationships when the coupling factor is 1. And what do we get? I2, 1 over r, good. N2 over n1, good. Vp cosine of omega t. V1 is Vp cosine of omega t. All right. So the good thing about this is this equation shows us if the coupling factor is not perfectly 1, like in our simulation, let's say we even have it 0.999, so pretty close to 1, this term here is still a non-zero number and kind of messes with our amplitude, right? Same with here. It starts phase shifting the current relative to the input voltage, right? So a coupling factor, you can imagine if we had a coupling factor of 0.9 even, or 0.8, this is really an issue, right? But let's say even with a coupling factor of 0.999, we will get issues. Okay, so let's kind of examine this. So we see that this omega minus 1, omega 1 minus k squared, n2 squared, n1 squared, squared L1, this is kind of our problem child right here. This is the one that's causing non-ideal terms for both the amplitude and the phase, okay? All right, so what is it telling us? Sometimes what's nice is that we look at this math, it looks horrible, we don't have intuition on yet it helps give us intuition, right? If we just kind of inspect it closely. And that's the nice thing about knowing both the practical and the theoretical. All right, so obviously we want k closer to 1. So we're going to set in our analysis k as 0.999, right? Okay, so we want k equals 1. That depends on the physical, of course, build of the transformer, right? And it seems like if we look at this, we want L1 to be as small as possible. I mean, omega is just whatever your line frequency is. We can't change that, like 60 hertz or 377 radians per second. The N2 over N1 is just, whatever spec your transformer is. But maybe you can change the L1. For example, what does changing L1 do? Well, let's say you have a turns ratio of N1 to N2, or I want a 10 to 1. So N2 is 10 times bigger than N1. Well, do I use 10 turns in 1 turn, or do I use 100 turns in 10 turns? Well, if I use 100 turns in 10 turns, I actually would have a bigger L1. Okay, and so that's kind of the physical correlation for how inductance could change even though your ratio is the same. Okay, so it seems like we want an L1 closer to 0. Now recall the mutual inductance. Remember that mutual inductance is the relationship between di dt to V1. That's the mutual inductance, or V2 is di1 dt to V2, right? So that mutual inductance, the bigger it is, the more powerful your rate of change of current on one side affects the other side. Okay, good. Now, if L1 is too small, what happens? You don't get a good transformer relationship. The transformer physically won't work, right? And also, I1 will be very large, right? So can you imagine the inductance is like a bigger water wheel? If you don't have very much inductance on this side, right? If you don't have very much inductance, you can think that this current is going to actually be quite big because this turns into more and more like a short, right? And so now, yeah, you have this offsetting, but this current amplitude is going crazy if this goes really small, right? So that's not good. So L1, you kind of have this compete, like in all engineering, you have this kind of competition. Sure, if I want a good ratio, right? If I want a good N2 over N1 behavior, I need L1 small. But we also know that if L1's too small, the transformer just doesn't work in general, and I get too crazy currents in here, okay? Well, what happens if L1 is too large? Well, if L1 is too large, the transformer, you can see, becomes less ideal even if the coupling factor is close to 1, right? So that's the trade-off we're playing here, right? There's a sweet spot of L1. And so let's look at some good transformer scenarios. Let's say you have a step-up transformer where you want the output voltage to be bigger than the input voltage. Well, if you have a big voltage here, you want a big resistor here to match it. That makes sense, right? So that you have reasonable currents. And then your inductance will also be reasonable, okay? If you do a step down, well, what does a step down do? It drops the voltage but increases the current. Well, if you're trying to increase the current, you want a small resistance here so that it matches, right? Okay, so small. So again, you would get a reasonable inductance. Okay, well, what's a bad scenario then? A bad scenario would be, let's say you have a step-up transformer, so you make V large, but then you also have a tiny R. That's not good because you're going to have a large voltage. You're going to get a huge current in here. And that means you're going to need a tiny inductance on this side, which might be impractical. And you're going to get huge currents on I1. That's also not so great, right? Okay. And then what about a step down? Well, if you have a step down and you're expecting a larger current here, but let's say you had a large R, the problem is you're not even going to get that much current coming out of this thing. And you would need a huge inductance to kind of drop down this current in order to do that, right? So these are like the bad transformer scenarios. These are good transformer scenarios. We can still pick an L that would work in theory, right, according to this theory, but it might not be practical. Okay, so what we did was I wrote a Matlab script. And what I did was I said, okay, can I choose a bunch of L's? So look at this guy here. This is essentially the ratio, right? Can I choose a bunch of L's and then just compare this to just my ideal ratio, right? Okay. And so what I did was I just plotted a bunch of L's and checked it, right? I gave it an example R and an example transformer ratio and then compared it against ideal. And what I found was this. I found that if I choose a small resistance and a small, this is the step down and then the small resistance, right? This is the step down and the small, sorry, let me get that right. This is the step down and the big resistance, right? So that's this quadrant. And then over here is the step up and the tiny resistance, right? So I have resistance here and transformer ratio here. Okay, here I have a step down but a small resistance, so that is this one. And here I have a step up, right, a 10-to-1 and a large resistance, that's here. So you can see the inductance values that I got are kind of reasonable, 0.89, 0.1, okay, good. But the inductances here are crazy. To get a step down and a large resistance, I need a huge inductance. That's not good, right? This is really not good, right? I mean, this might be realizable, but getting teeny inductances, especially when they depend on the number of turns squared, that's hard to do. So this is bad. This is a step up with a very small resistance, right? And how did I do this? Like I said, I chose L's so that I chose a smaller percent ratio error. And I also chose a small percent phase lag, right? Because we can see that in this equation, we can choose an L such that we get a small phase lag as well. Okay, we want this as close to 0 as well. Okay, all right. So how did we do this? How do we punch this in MATLAB? And then what is the effect of choosing these numbers? What is the effect of choosing these numbers in the simulation? Okay, so what we're going to do is we're going to go to the simulation. We're going to look at MATLAB. We're going to look at the simulations, just kind of play with the numbers a little bit. And then we're going to come back. And if you're still interested, we can look at the proof, right? We can look at how did we even get this insane equation, and some differential equations might come in. I know your eyes might gloss over, but for those who are interested, stick around, right? Might learn something. Okay, let's go and switch over. So let's go over here. All right, so here's my Matlab plot or Matlab script. And you look at this and like, what am I doing here? I'm plotting I'm creating a huge log space of range from 10 to the -10 to 10 to the 10 and making 100 points, right? I'm setting my coupling factor as 0.99. And in this case, I'm saying, let's make the ratio N2 over N1 10. So it's a step up. And let's say omega is corresponding to 60. So this is about 377. And I have a small resistance. So this is one of the bad cases, right? So in the bad cases with a step up of 10 and a small resistance, I should get a very small inductance that would work, okay? Now this is my voltage ratio, okay? So this is that amplitude minus the V peak. And what I did is I compared this voltage ratio to the ideal ratio. The ideal ratio in this case would be 10, right? So I said 10 minus whatever this gives me divided by 10. So it's a percent difference between ideal and actual voltage ratio. Okay, I also plotted what the phase lag would be. So I plotted that negative atan, right? I divided it by 2 pi so that it's actually a percentage of a cycle, right? So how much of a period it actually shifts. And then I plotted it. I plotted on a log scale and a log scale. And for fun, I actually plotted the inductance on a linear scale just to highlight why we would want to go to a log scale in this case. Okay, so I plot that cost, the phase lag. Okay, so let's run this guy. All right, so let's look at these 3 figures. Okay, so the first figure is showing what? It is showing the percent difference between ideal and actual voltage ratio for inductance. So these are all different, very small inductances to very large inductances. And I want 0. I want something as close to 0 error as possible. Okay, so that could be somewhere around here. All right, and you can see I can click a point and look at this, 0.001. I can just shift the dot, 0.0001. Okay, so around here, this was actually the point I chose, 0.0001 for the inductance, which gives me a 1% error on that voltage ratio. So that's pretty good. I could look at the phase lag and I go, well, if I chose 0.001, what do I get on the phase lag? Let's see, 0.001, it looks like it is right there. See the same inductance value, 0.0018, 0.0018. Okay, good. So that means it gives me a phase area less than 2% and a voltage ratio less than 2%. Nice. By the way, I plotted the same plot on the linear. Look at this, linear scale. Remember we talked about the log versus linear? Look how I get a huge range on the log and nice resolution. Whereas this, I get a huge range on the linear, no resolution. Like, what am I going to do here? I can't pick these nice values cleanly, right? So you can see in this case, a linear scale is useless. So I just plotted that just for fun, just to kind of hit home that linear versus log scale. Anyways, what I could do is I could take these values and go over and see what I get. So let's go to the simulator. So 0.001, and I have a ratio of 10 and a resistance of 0.1. So let's go over here. So we can say the resistance here is 0.1. Okay, so small resistance and a ratio of 10. Good, I have it. And I can put in my values 0.0001 for the inductance and a coupling factor of 0.99. Okay, so let's run this. Reset, run. And what do I notice? I see that my input is 120 volts and I get 1.2 kilovolts on the output. That's good. That's a 10-to-1 step up. That's exactly what we want. And what do we have here? We have 120 kiloamps RMS, which is just crazy and impractical. But I also get 12 kiloamps RMS on the output. So at least it's behaving like an ideal transformer. Now, like I said, this is a bad situation. We don't want to be doing this, right? For the various reasons. Look, you don't want to have 120 kiloamps RMS. It's totally unreasonable. But at least because of the choice of inductance, which is also unreasonable, 0.0001, it's crazy small. It is at least behaving like an ideal transformer, okay? Everything's nice. We're all happy here, okay? Now, let's say we had this same horrible transformer situation and I didn't pick the inductance well. So let's say I picked, let's say here, right? So I could pick here, right there. And what is this saying? If I even went up to 0.0029, I would expect an error of 60%, right? So instead of a 10-to-1, it would be a 6-to-1 kind of thing, right? All right, over here, what do we have? If I get the same number, so I'm gonna try to find it, I would get a phase lag, here it is, of 18%. So I'd be phase shifted by 18%. I'd be lagging. Let's try it. So I'm going to go over here and I'm going to put in, what did we say? 0.0029. Okay, and I'll hit apply. And let's just double check I got the right numbers, 0.0029 and 0.0029. Okay, all right, I'm going to reset it and run it. Whoops, run it. Okay, look at this. I don't get that same 10 to 1 step up. Look how the step up goes to 500 instead of 1.2 instead of 10 to 1, right? So that's good. And then look at the current. The current, do I get a 10 to 1 step down? I still get a 10 to 1 step down, so that's nice. Okay, so that's good. But the voltage is not behaving exactly the way we want it. It's not performing ideal. Now, what about the phase lag? What about the phase lag? The phase lag we said was about 18%. Okay, so if we look over here, remember I2 and V2 are in phase because they are just a resistor. So here V2 is the red line. Look how the red line, I'm going to pause it. So the I2 is in phase with the V2, and look how the V2 is lagging the green primary by about 18%. If it was 25%, this 0 point would be exactly under the peak of the input voltage here. Okay, so this is hopefully hitting home our trigonometry stuff. So there's a lot of concepts that we've learned already that are really coming into play here. Logarithms, voltage, RMS, even 120, 170 to 120. So this is kind of nice, right? Okay, we can even do one more. Let's do one more. So we can come over back to let's go pick a good case. So what was a good case? Well, a good case would be, let's say a 10 to 1 step up, but now the resistance is 100. So high step up, but also a high resistance. And we can play the same game. Okay, so I hit this run and I create my 3 plots. Okay, and here they are. Again, the linear scale is crap. That's not going to be useful. And here's the phase, and here's the voltage ratio error. Okay, so this is error in phase. This is how much your phase lagged. So it looks like we'd like to pick an inductance value of, let's say, 0.1, what does it say? 0.123 inductance will give you a 0.5% error. Not too bad. If I come over here, let me drag this, 0.123 value of inductance, same value of inductance will give me a 1% error in phase. Okay, let's try it. So if I go over here and to 0.123, so this has to go to 100 now. So this is 100. Okay, and this is 0.123 now, 0.123. Okay, I run it. Same ratio, right? Same 10 to 1 ratio. Okay. And what do we get? Yep, 120 to 1.2 kilovolts RMS. Yes, so we're getting a large jump in 10 to 1 V2. And let's look at this, 120 amps down to 12 amps. Good, and all reasonable currents, right? Nothing like in the kiloamp range. That's nutty, okay? I mean, even still 120 amps is still a lot of current, ladies and gentlemen, but much better than the other situation. Okay, so this is good. This is behaving ideal again. And look, nearly zero phase shifting, right? Everything's nice in phase. Yay, this is all behaving ideal with that right choice of inductor and resistance and load. So everything is matched, right? Now, again, let's go over here and choose a poor value of inductance, right? So let's go in the middle here. So you can see a poor value of inductance might be 3 point something. So what do we get? 3.2. Okay, so if we put in 3.2, we're going to get a 60% error in the voltage ratio, and we're going to get an 18% lag. Okay, let's try it. So 3.2. So I'm still maintaining the transformer step up, and let's just see what happens. What do we get? Again, look at this. The voltage does not follow the 10 to 1. It's much less, 460 volts, right? We get that 60% error, right? And then now the current, yeah, okay, the current still maintains a nice ideal or is close to the ideal relationship, 10 to 1 step down. But look at the phase lag. Again, if I pause it, the phase lag of V2, which remember V2, which is here, or VS, and then IS are in sync because it's just a resistor. So if I can compare the phase lag of V2 to the voltage V1, that's equivalent to looking at the phase lag of I2 or IS to V1. And here we can see, look, nearly 25% or 18%, right? Okay, so here's the peak. This would be 25%. If this peak or this 0 point was just moved over, it'd be 25%. Okay, so I hope this kind of hits home that you need to choose, if we're dealing with a transformer, it's not just choosing the turns ratio alone and forgetting. We have to consider what the load is, we have to consider what our current limits are, the voltage limits, and we have to consider what our ratio is and the primary inductance. I mean, the secondary inductance is dependent on the primary inductance and the turns ratio. So once you know one, you know the other. And also the coupling coefficient. So all these factors come into play, and that's why these engineers that make these and the manufacturers that make these transformers, they spend a lot of time analyzing this. There's so much engineering and development that goes into these simple transformers, which, yeah, it's only copper and steel. But it's amazing. It's actually quite amazing, all the math and physics that goes into this to get things to perform the way they should be. Okay, so let's go back to the doc cam here. Now, if you're still interested, if I haven't lost you, what I'd like to do is then show you now where this I2, this crazy I2 equation came from. So I'm going to bring that back. So here's our crazy I2 equation. Okay, crazy amplitude and this phase thing. And you're like, wow, where did that come from? Well, let's start. So I have our transformer, and we know V1 is a VP cosine of omega t. We have our Ohm's law, V2 equals I2R. And we also know that we can write our self-inductance equations, right? So let's double check this. V1, so remember this V1 is the same as this V1 over here, right? So this is also V1. So you can see by the self-inductance, I1 is going into the positive terminal, so that's positive. And look at I2. I2 is leaving V2, so that's negative, good. And what else do we have? We have I2. I2 is leaving its dot, and V1 positive is touching its dot, so that's a negative. And I1 is entering its dot, but V2 positive touching, that's a positive. Now, if you remember before, what we did was we solved for I1 and plugged it in here. That was in the last lecture, okay? And we got V2 as a function of just I2, okay, and V1, and that's this guy here. So I'm writing this out. And so you get I di2 dt, and then you get this term, and you get plus k n2 n1. Now, remember, in this case, if you look at it carefully, if k equals perfectly 1, can you remember these cancel? And you're actually just left with the ideal transformer relationship. Okay, so it's a good little check that we did that correctly. Good. Okay, but this time we're not going to leave it as one. We're just going to leave it as a variable. Okay. Now remember, the ratio of L2 and L1 is the ratio of N2 and N1 squared. Good. So I'm just going to substitute that in just to get everything in terms of L1 because that's what the simulation had. Okay. So yeah, that makes it a little bit messy. Okay, but nothing too bad. Okay, and the rest is just a little manipulation. Then what I'm doing here is I'm going, okay, well, di, what do I have here? I have the Ohm's law, so I know V2 is the Ohm's law, so I bring that here. This is still the same, good. And this di2 dt, what am I doing? I'm pulling it out, and look, L1, good. N2 over N1 squared, good. They're on both sides. And I have a 1 minus k squared, and I put an extra negative because it's really k squared minus 1, but I put 1 minus k squared minus here, and you'll see why I did that later. Okay, let's keep going. Okay, just chugging along. I'm going to isolate di2 dt, right? And you can see now why I put that minus so that all these terms are positive. Okay, so what happens here? So if I have this di2 dt, okay, and I want it by itself, what I had to do was I said, okay, I'm going to bring this over to one side. Okay, I'm going to bring it over to the R2 side. And now the R is going to have to be divided by this thing, 1 minus k squared N2 squared, right? L1, good. And this guy here, which stays, is going to have to also be divided by this one. But by bringing it over to the right, you can see I made it positive. So that's nice. Everything's positive. Okay, again, it's like, oh gosh, you can always pause the video and look, make sure all my terms are correct. And don't forget, this V1 is oscillatory. I have a di2 dt, I have an I2, and I have a bvp cosine omega t. If this was a constant, we would know how to solve this. This is a first order differential equation, and we'd have e to the minus k1 e to the st plus k2. That would be the solution for I2. Not the case in this scenario because we have an oscillatory voltage input. And so in this case, here's what the general solution would be. Instead of here you have dx dt plus ax of t plus b cosine omega t. Instead of something like this, e to the minus t, you also have this. You have an oscillatory component. Because you imagine if this is oscillatory, this will also be oscillatory. Now, let's look at, this is the general solution. This is the guess, which is kind of crazy, for this differential equation. So like I said, when we solve these first order differential equations, you're only getting the teeny tiny tip of the iceberg. It gets much crazier, right? This is not even second order. So anyways, this is the solution to this problem here, right? If I were to take this and its derivative, right, and I put it back in this equation, this would be happy, if that makes sense. Now let's look at this closely. You can see that this term, e to the minus at, you know what happens to this. It decays to zero with time. So we're just going to even ignore that, right? Because we're going to look at this in a kind of a AC steady state. Now we can see this, look at this. It's an amplitude and we have a cosine. So this thing oscillates, all right? And if we look carefully, what's B, what's A, and what's omega, right? And look at this phi here. That's the tan inverse of omega over A. So we got to be careful here. Omega is the electrical frequency of my input. A is going to be related to this guy. In fact, it's exactly this guy. So that term and that term is this guy. And this B is this guy with the VP in it, right? Okay, because we have an A, B cosine omega t. Exactly the same form. So we can just match, pattern match, right? So that's nice. And by the way, where did I get this equation? Googled. I think it was an MIT open courseware, something like this. But this is just the solution to that, right? Okay, so if I look at this, A is this one, r over 1 minus k squared n2 squared over n1 squared L1, good. B is this k n2 over n1 1 minus k squared n2 over n1 squared L1 times the V peak, right? Good. And let's just solve for this guy first. Well, what do? I mean, this is just algebra here. B, which is this guy divided by the square root of a squared plus omega squared. Okay, so I just plug it in, no problem. I can combine these. I can multiply the top and bottom of omega squared by this thing squared. Okay, good. Now notice what I got going on. Check it out. It looks like this term here squared and a square root, they're going to cancel. So I get this 1 minus k squared n2 over n1 squared L1 on the bottom. But check it out, in the B term, I also have the same denominator. So that actually clears out. Nice. So the B over square root of a squared plus omega squared here is just this, okay, times, of course, VP, all right? And what about the omega A that's going to go in the phase? Well, we just take literally omega divided by this. So it's just the inverse. And that results in that equation, which is the same one as before, right? Where phi is this guy, and this guy is the tan inverse of whatever that is. I know it's kind of crazy, but if you stuck around, this is how I got those equations. And you better believe when I figured this out and then started punching in, playing with MATLAB, and I was also collaborating with Dr. Tony Snell, and we were like, wow, is this true? Is this true? Very exciting. It was like, yes, it just was confidence building. So we're sharing this result with you guys. We think it's kind of fun and shows how sometimes the math, just grinding out the math, can give us better physical intuition, right? And vice versa. So I hope you enjoyed. I know this is a lot, but if you have any questions, of course, I'm willing to answer them in class. And yeah, have a great day.